It's my pleasure to chair the first paper session of the day. The paper session is titled Geospatial AI and Data Science for Sustainability Solutions. And the first paper, titled Fine-Tuning Mobile Net Neural Networks for Oil Spill Detection, is going to be presented by Caixia Wang and Andrew Coulson, both from the University of Alaska at Anchorage. So I invite them to the stage to present.
Thank you. Good morning, everyone. So I spare my student there, so I'm going to take the stand and talk about our work. This is a work Andy, Coulson, and I worked recently. So we're focused on the oil spill detection. By the way, my name is Caixia Wang. So I'm from the University of Alaska, Anchorage, from the Department of Geomatics, which may be a little alien name for everybody, but it's basically survey and mapping. So this work is very fortunately funded by the Colleague Phillips Arctic Science and Engineering Endowment, as well as the NSF. So I think I'm gonna echo what Barbara mentioned about, we have to show the services or the benefit from geospatial work we did and how this is going to benefit the agencies, especially in Alaska. So I'm going to talk about that more in terms of the motivation. All right, so why oil spill detection is important, why we are working on this for a couple of months for now. As you all will, oil spill pose a substantial threat to the sea ecosystems among all the types of marine pollutions. And recently, the risk has been escalated by the surge in oil and gas exploration, as well as the shipping activities, especially in very fragile Arctic region. So those, as a result, those pose a very pressing need for efficient monitoring in open water to enable us to provide a timely response efforts so that we can mitigate the potentially disastrous the consequences from the oil spill in those areas. So that's why we are proposing that type of efficient approach in this work. So we have done quite a bit already recently in different areas. For instance, that we are using the in situ type of method by using specialized sensors on the vessels or on the airborne platforms. We're already able to do such type of monitoring. However, as we all know that this type of methods are very time limited and also limited to certain observation conditions. For instance, like the image on your left, as you can tell, there's a glare of the sunlight. So that is gonna obscure those edges for the test area. So it's hard to detect it. On the other hand, it's very labor intensive. So that is, the limitations we have to face. However, you might argue remote sensing technologies can, help us to monitor in broad areas. Especially for Alaska, we have a lot of cloud covering in the area we want to monitor in. So SAR, synthetic aperture radar, actually can help us to monitor in those areas independent of weather. But using the traditional pattern recognition for image processing analysis does have challenges, as you see on the images on your right side, the third one. It's not a oil spill slick on the water. It's basically, it's like a similar phenomena showing as that black area. So from the traditional pattern recognition, it will be misclassified as the oil spill slick, but instead it's actually the type of similar phenomena from the shallow wave behind the structure or behind the topographic features, such type of similar phenomena. So as you can tell, compared with the true actually oil spill from the SAR images, which is showing in the middle, they are very like each other. So how can we, so that means that remote sensing technologies, even with the SAR technology here for very suitable for Alaska, so we still have a lot of challenges to solve. So that's what we would like to propose in this work. So here is a method. So we are based on our method using the pre-trained models. So we don't build up our model from the scratch, which is a Mobilenet. So I will talk a little bit about this model for a bit. And then we are transfer this model by using our own data sets through the transfer learning and fine-tune it to our application. And you will see how efficient this can make the pre-trained model to fit our applications. And then we can show you some of the evaluation through the test data at the end. So how many of you worked with Mobilenet? Raise your hand. So one. So two, great. So Mobilenet, it's a neural network, convolutional neural network model, and it's originally developed for object detection in mobile and embedded based computer vision applications. So the categories or classes they are aiming to detect, including like the object, for instance, the buses or pedestrians or like landmarks. So those type of objects they are trying to detect. So I posted the paper there, so feel free to check it out. And it's not intended to, it doesn't have any training data to train the model for our application. However, the architecture is really efficient. So the Mobilenet is characterized by its depth-wise separable convolution. So that includes the depth-wise as well as the point-wise convolution. And this is a very talented innovation because by using those two types of convolution, the model is going to become quite a bit relatively small compared with the popular CNN models. At the same time, the models can still perform very well through their the training data as well as the performance. So to give you a sense of how small this data is, this model will be, I'm using the VGG16 to compare with the Mobilenet by using the size and the parameters. So 17 megabyte compared with 553 megabytes in terms of the size of the model, and then parameters, it's only have 4.2 billion compared with 138 billion. So quite a bit small. That's why it's very attractive for us, for our application. I'm not gonna bore you with this flow chart. It's directly copied from the paper, so you feel free to look into it. And so I'm gonna see how we can train this model to transfer to our applications. So the data we actually using for this work has, they are all true color images, so they only have 3 band. But we do want to include images with varieties. So that means that from different perspectives. So we include images from the ground view as well as the airborne view, including space and area. Some of the views are bird view, some of the views are oblique views. So those are the variations we want to include it. And also the images not only contain the water features, they also contain the vegetations, some of them contain the boats, some of them don't. and some of them also contain the coastal lines. So we want to have those varieties in our training data as well as our test data, and to see how this model, after we transfer it, how this model performs. And in total, we have 436 images, so less than 500 images. So that include the images from Kaggle, which is an open source, as well as some images that we manually allocated. So all of those images, we want to have this balanced categories. So that means that half of those will be represent spill, half of those will represent no spill images. And then with all those 436 images, so we randomly sampled the data into 3 categories: the training, 75%, the validation, 15%, and the test data, which is 10%. So the test data are not used for training, so we can evaluate our performance, the model performance independently. So the transfer learning, this process is quite a bit simple, but I think in order to make it work, you have to be careful in terms of the selection of your data for the transfer learning, as well as how you're gonna, the number of the data, depending on the CNN model you choose. The process, so there are very nuances in terms of steps, but I would like to mention 3 steps which are critical for transfer learning. The first one, the images have to be pre-processed to meet the requirement of the model you choose. For the Mobilenet, it's quite a bit straightforward, so we just need to take care of the size of the images. Another thing is, as we all know, the CNN models are layered architectures, and then the lower layers are learning from the training data for the elementary type of features. For instance, the colors, corners, those like very fundamental learning information to bring to the model. And the higher layers are going to be combine those elementary features to formalize the features that we are interested, right? So you need to select the layers from the higher layers in the architectures, but what are those higher layers we should select for fine-tuning is a huge question. So in our work, we did through try and see. So if you know that there's an automatic way to do so, I'm allowed to talk with you. So we tried different ways, and then we finalize what are the layers we are going to use for fine-tuning. So it's end up, we use all the layers after 22, and then we're doing the transfer learning. The last part, because Mobilenet is designed to classify 1,000 classes, but ours only 2 classes. So we have to make that revision to fit our application. So those are the critical steps for transfer learning step. So to give you a sense of it, so I just copied the last part of the transferred or fine-tuned Mobilenet. As you can tell, the total parameters becomes to 3.2, even smaller than the original Mobilenet model. And there are non-trainable parameters, which represent those layers that we want to preserve. And then there are trainable parameters, which represent those layers that actually we fine-tune to our applications. So give you that kind of summary of the result of the transfer learning. All right, so I'm going to jump directly to the result because the entire process is quite a bit straightforward. They only just, those 3 steps, if you are able to make them, efficient for your applications, that would make it, quite a bit straightforward. So compare with our final model, with the popular CNN models, as you can tell, that our model is even smaller, only 12 megabyte compared with even Mobilenet, and 3.2 billion parameters. So which is quite a bit for our future work, quite a bit small. However, the accuracy, we are very happy with it. So I'm using this very traditional confusion matrix to show the metrics for those two classes. So overall accuracy is about 93%. So we're using 43 test images. So just to give you a sense of how efficient this work is, since we're not doing the model from the scratch, and we're only using less than 500 images, and in terms of 75% training data, so which is less than 300 images, just do the training part. So it's give 93% accuracy. So that's indicate the efficiency of this work. So I'm just to wrap it up for this preliminary work we have done. So it does. The work is based on the Mobilenet, which is relatively small but efficient. And we demonstrate that transfer learning is a very effective technique in CN model development for custom applications. So we don't build up our CN model from the scratch, which is really very costly, if you will, if you consider the training data. And they developed the Philo model we have, which is relatively small, and it can be potentially deployed on the web for real-time applications. So that's going to be in our next step. So that's why we choose Mobilenet, because we are going to deploy this model to a very computational constraint environment, and then present the work, the final result in real time. So it's require faster responses. But in order to do that, we also need to improve our model to handle larger, high-resolution images. As you can tell, we are detect one image at one scan, if you will. But for high-resolution large images, so we have to develop some method to scan the images, and in order to detect the oil spill area on the image. So that's going to be in the future work. So with that, I wrap up my presentation, and I'm happy to take any questions you may have. Thank you.